All right, so moving along, we're going to start lesson 6.2 today. Actually, it's only a one-day lesson, so we'll start and finish. Present my screen and we'll get started. Okay, so lesson 6.2, the natural base E. We're going to talk about simplifying, growth, decay, and graph. All right, so first off, just like pi and I are special numbers in math, so is E. It's known as the Euler or Euler's number. All right, so pi we know is approximately 3.14. We use that a lot in geometry class. I, we learned this year, imaginary number, I is equal to the square root of -1. And then we have E, okay, which we're going to be using our calculator anytime we're evaluating anything with E. But you can also know that it is approximately 2.718. Okay, and again, that's the approximation, that's rounded. So as x approaches infinity, 1 plus 1 over x raised to the x approaches E, which is approximately 2.718. All right, E is found on the calculator above the division sign. So I'll show that to you now. All right, if I pull up my calculator, let me clear everything. Okay, there we go. Right above the division symbol on the calculator, you see E, right? So to get to it, since it's a blue function, I hit the blue key, the second key, and then I hit the division button, I get E. Now if I push enter, you're going to get the decimal approximation, approximately 2.718281828, so on and so forth. Okay, so that is where E is on the calculator. All right, so to simplify, the nice thing is we just follow exponent rules. So if we're simplifying E to the second times E to the ninth, I don't know why that box keeps popping up all the time. But if I'm evaluating E to the second times E to the ninth, our exponent rule would be to add the exponents, right? If it was x to the second times x to the ninth, so it's E to the 2 plus 9, which is just E to the 11th. All right. I don't know why it's not letting me write anywhere lower than this right here. It's kind of odd. Okay, so E to the 11th. I'm going to write it out horizontally. E to the 2 plus 9 and E to the 11th. Now, it's just asking us to simplify these, so that's how we would leave it. I'm not asked to evaluate, so I'm not going to use my calculator and do E to the 11th and get a decimal approximation. Okay, the next one to simplify, well, first I can do 25 divided by 5, right, to just get a 5. And my bases are the same when I'm dividing. The exponent rule would be to subtract. So 25 divided by 5 is 5, and then it's E to the 11 minus 12, and that's going to leave you with 5E to the first, or just 5E. Okay, you don't have to write that exponent of 1. All right, the next one, power of a power. Everything inside the parenthesis has to be evaluated to the 5th power. So I could rewrite this as 2 to the 5th, and then E to negative 3x times 5. Multiply the exponents together. All right, 2 to the 5th is going to give you 32. So now I have 32 E to the negative 15, E to the negative 15x. Now, the very last thing is just to clean it up. I can't have negative exponents. So to turn that exponent into a positive, we know that we write the answer as 32 over over E to the positive 15x. Okay, the exponent becomes positive. I'm going to write that up here just so it's a little easier for me to see. E to the positive 15x would be your final. Okay? Okay, so let's keep on moving along. We have natural base functions, all right? Y equals AE raised to the RX. Now, when your A value is greater than 0 and your R value is greater than 0, that's going to be exponential growth. When your A value is greater than 0, but your R value is less than 0, that's going to be exponential decay. All right, so R is greater than 0, exponential growth. R is less than 0, exponential decay. Decay. All right, so it says here, tell whether each function represents exponential growth or decay, then graph the function. And we are going to be graphing using our graphing calculators. So first thing I want you to just get used to is listing the A and the R values. So A is 2.5 and R, okay, the R value up in the exponent with the X is a 1. All right, so since R is greater than 0, I know that this is growth. For the next problem, the A value is equal to a 1. The R value is equal to negative 0.2. Since the R value is less than 0, I know this is decay. All right. In order to graph, we are going to be using our graphing calculators. And just like we did for the graphing in day 1 of lesson 6.1, we'll make a table and then we'll plot those points. Okay. All right. So let me pull up my graphing calculator. Oh, let me erase some of, I didn't mean to erase all that, but that's okay. Okay, so I'm going to go to y equals, clear out that one. So the first one is 2.5, and then I need my e, so second division, e raised to the x. And I'm going to graph. Oh, let me zoom. Let me just do zoom standard for a second. Okay, you could do zoom standard. If you want to do zoom fit, you could do zoom fit as well. Okay, you can see it's exponential growth as we said it was. And then I'm going to hit second graph to get to the table. And you can just jot down some of those values, and I'll do the same over to the side. Let me pull this up just a little bit. Okay, so for my table of values for number 1, I'm probably going to list -2, and then it's 0.334 approximately. These are approximations. -1 is 0.92 approximately. 0 is 2.5 exactly. 1 is 6.8, and 2 is 18. We'll say 5. Right, so now I can plot those points, or maybe not all of them, but enough of them to get the shape of the graph. So -2, and this is like right above the x-axis. -1, and this is right below +1. 0, 2.5, and then 1, 6.8. And then I'm not going to graph the 2, 18. But you can see that you have an exponential growth function. All right, let's graph the next one, number 2. Oh. Okay, so y equals, clear that out. So the next one is e. Oh, I don't think I pushed the second division. There we go. E raised to the -0.2x. And then hit graph. I can see it's exponential decay. I'm going to go to my table to get some values to jot down. Where can I put this? I'll put it over here for just a second. All right, so I have x and y values. So -2, and that's approximately 1.5. -1, and that's approximately 1.2. 0, 1, 1, and 0.9, or we'll say 0.8, and then 2.7. Okay, and that will be enough. All right, so let me get rid of my calculator. Let's graph those points. So -2 and 1.5. Then -1 and 1.2, just coming down slightly. Come on. And then 0, 1. And then 1.8. And then 2.7. So it's slightly going down. Okay. Now, two key points on graph. So take a look at the functions, take a look at the table of values. What do you think 2 key points are? Well, I erased the A values and the R values, but if I hadn't erased them, or maybe if you're looking at your sheet, you're noticing the 2 key points, oh, I can't write any lower, are 0, comma A, and then 1, comma AE. All right, so if you look, 0, comma the A value, and then 1, comma the AE value are both listed. Okay, so just going back up here, A was 2.5 and R was 1 for this problem. A was 1 and R was negative 0.2. So again, 0, comma A, 0, and then the A value, 0, and the A value, and then 1, and then E times A. So if I take my A value and multiply by E, that's going to give me 6.8. If I take E and multiply by 1, that's going to give me 0.8. All right, so that would be 2 key points for graphing purposes. Okay. All right, let's move on. Use the properties of exponents to rewrite the function in terms of, or in the form of y equals a plus or minus r raised to t, then find the percent of change. So we actually did a problem like this the other day, but now we're going to have e instead of just our exponential growth and decay models of 1 plus or minus r, but we still want to get it into that form. Okay, so using the laws of exponents, I'm first going to rewrite it as 2 and then times e raised to the 0.4 and then that raised to the t. Okay, so think about rules of exponents. If I wanted to, I can multiply these exponents back together to get what was originally written. All right, so I'm just rewriting by using laws of exponents and simplifying, but getting something that's equivalent to what was originally given. So this was power of a power property that was used. All right, so then what I'm going to do is I'm going to evaluate e to the 0.4 on my calculator. So pull up your calculators. Pull it down here. Okay, so there you go, a little bit bigger. So I want to evaluate on my calculator e, so second divided by raised to the 0.4, push enter, and I'm going to write that whole decimal down inside of where the parentheses are now. Okay, so it's going to be y equals 2, and then instead of e raised to the 0.4, it's going to be 1.491824698 raised to the t. So again, this next line is equivalent to what's right above. Now I'm very close to that y equals a times the quantity 1 plus or minus r raised to the t. Okay, I have my t, I have my variable by itself. My a value is a 2. Inside parentheses, I just need to write this as 1 plus something or 1 minus something. All right, since inside the parentheses is a number larger than 1, I know it's exponential growth, which means it's going to match that, oh goodness, it's going to match that 1 plus r model. Okay, so I have y equals 2, and then it's going to be 1 plus something raised to the t. Well, what do I have to add to 1 to get 1.49182? I have to add 0.491824698, right? If I add 1 plus that decimal, I get 1.4982249. So at this point, I will now round. So I'm going to make that y equals 2, 1 plus, and we're going to round that to 0.49 raised to the t. So now if you look, you're in that y equals a 1 plus r raised to the t model. Y equals 2, 1 plus 0.49 to the t. And the question was asking for the percent of change. Well, my R value is approximately 0.49. So my growth, my growth percent is 49%. Okay. All right. So that was that problem, which is similar to one of the other problems we saw in a previous lesson. Okay. So looking at an exponential growth decay graph, where do you see the principal initial amount? Okay. So when we graph a function, and we probably could go back, let me see if I can pull anything up on my graphing calculator. All right. Where do you see the initial function, the a value? So this is the graph. Let me go back up for this graph right here. Okay. Its a value is a 1. So think about that. The a value of this function, of this equation, is a 1. So where do you see that on the graph? Do you notice the y-intercept is a 1? All right. So to answer this question, looking at an exponential growth decay function, where do you see the principal or the initial amount? Oh, let me get my pen. You're going to see the principal or initial amount at the y-intercept. All right. When x equals 0, because in this case, time, right? X is going to represent your time. And when the time is 0, that's your initial amount. So when x is 0, that's your y-intercept. That's where you're going to see the initial amount. And that's why one of the key points for graphing is 0, comma a. Okay, because when x is 0, the y value is going to be a. That's your y-intercept. Okay. Continuously compounded interest, which we don't really do much work with, but I do want you just to be exposed. So the equation is a equals p times e raised to the RT. Still the same variables, really. So a is your amounts, p is your principal, r is your interest rate, and t is your time. Okay. And then just a quick reminder, which might help you with some homework problems, to find an inverse. Remember, you swap the x and the y and then solve for y. We did that in the last chapter. So that's just a quick reminder before you guys work on some book problems. Okay. So that is it for lesson 6.2. It's only a one-day lesson. So I'll see you back here for lesson 6.3. Bye.